Introduction. When the universe refuses to make sense, astronomers don't lose sleep because they're scared of the dark. They lose sleep because they're genuinely confused, because out there in the vast expanse of space, we've discovered things that simply shouldn't exist according to everything we know about physics, chemistry, and the cosmos. These aren't theoretical speculations or philosophical musings. These are real, verified observations, phenomena we've measured with precision instruments, documented across multiple wavelengths of light, and confirmed by independent research teams around the world. They're happening right now, doing whatever strange thing they do, and we have absolutely no idea why. Over the past several decades, as our telescopes have evolved from simple optical instruments to sophisticated arrays spanning continents and orbiting in space, we've stumbled across discoveries that have left the scientific community genuinely baffled. Some challenge our fundamental understanding of physics. Others suggest processes in the universe we haven't even begun to comprehend. And some are just inexplicably weird. This is the story of those discoveries, the cosmic mysteries that keep astronomers awake at night, staring at data that refuses to make sense. The WASP signal. A message from nowhere. On August 15, 1977, Jerry Emin was doing what astronomers do, reviewing data, looking for patterns, searching for anything unusual in the cosmic noise. He was working with the Big Ear radio telescope at Ohio State University, part of the Search for Extraterrestrial Intelligence project. The telescope scanned the sky methodically, day after day, listening for radio signals that might indicate intelligent life somewhere among the stars. Most days brought nothing but background noise, the random static of the universe. But on this particular day, Emin saw something that made him grab a red pen and scrawl "wow" in the margin of the computer printout. That exclamation gave the signal its name, and nearly 50 years later, we still don't know what caused it. The signal lasted exactly 72 seconds. During that brief window, it was 30 times stronger than the background noise, an enormous spike that stood out unmistakably from everything around it. It came from a specific direction in the constellation Sagittarius. And here's what makes it truly fascinating. The signal's frequency was centered around 1420 MHz. Why does that matter? Because 1420 MHz is the hydrogen line, a natural frequency associated with neutral hydrogen atoms. Hydrogen is the most abundant element in the universe, making up about 75% of all normal matter. If you were an alien civilization trying to send a signal that other technological civilizations might recognize, choosing a frequency related to hydrogen would be brilliant. It's like using a universal language based on something everyone in the universe would know. The Big Ear telescope had two receivers that scanned the same patch of sky, with a 3-minute delay between them. This design was intentional, providing confirmation that signals were real and not just interference. The WASP signal appeared on the first receiver but not the second. This means it lasted less than 3 minutes, probably close to the 72 seconds indicated by the data, and then vanished completely. Since 1977, astronomers have returned to that exact location in the sky dozens of times. They've used more powerful telescopes than the Big Ear. They've listened at the same frequency and scanned nearby frequencies. They've devoted thousands of hours to searching for any sign of the signal returning. The result? Nothing. Complete silence. The WASP signal was a what-if event. The uncertainty surrounding this signal is profound. It could have been artificial, a deliberate transmission from an intelligent source. Or it could have been natural, some cosmic phenomenon we don't understand. The Big Ear telescope's design, while excellent for its time, couldn't pinpoint locations with modern precision. We know the general direction, but not the specific source. Scientists have proposed natural explanations. In 2016, researcher Antonio Paris suggested that two comets 266P, Christensen, and P. 2008Y2 were passing through that region of space at the time. Comets can emit radio waves when solar wind interacts with the hydrogen clouds in their tails, potentially creating signals detectable from Earth. But there's a significant problem with the comet's theory. Bandwidth. The WASP signal was incredibly narrowband, occupying a very specific frequency range. Natural sources typically produce signals spread across broader frequency ranges. The narrowness of the WASP signal is more consistent with an artificial source, something deliberately transmitting on a chosen frequency. much like our own radio stations. Other scientists suggested terrestrial interference, a satellite, aircraft, or ground-based transmitter that happened to send a signal at precisely the right time and frequency. But the Big Ear telescope was specifically designed to filter out terrestrial interference. The signal came from a direction inconsistent with any known satellite or aircraft path at the time. Moreover, the signal's characteristics, its frequency, duration, and intensity pattern didn't match typical interference. So, what was it? Nearly 50 years later, the WASP signal remains one of the most intriguing unexplained observations in SETI history. The fact that it never repeated is simultaneously frustrating and significant. If it was an alien civilization, why transmit only once? Perhaps they were using a lighthouse strategy, sweeping a powerful beam across the galaxy, and we happened to catch it for a brief moment. Perhaps it was a what-I'm broadcast, a cosmic message sent out into the void. Perhaps it wasn't meant for us at all, just accidental spillover from communication between two distant points. Or perhaps it wasn't aliens. Perhaps it was some natural phenomenon we've never encountered before or since. The universe is full of processes that emit radio waves, pulsars, quasars, magnetars, supernova remnants. We're constantly discovering new types of radio sources. Maybe the WASP signal was something natural that we simply haven't seen again. The truth is, we may never know. The signal lasted 70 seconds in 1977 and never returned. It's a mystery frozen in time, a single data point that refuses to provide context. But it's also a powerful reminder of how much remains unexplained about the universe. Somewhere out there, in the direction of Sagittarius, something sent out a powerful narrowband radio signal, and we happen to be listening at exactly the right moment. That's either the most incredible coincidence in the history of astronomy, or evidence of something extraordinary. Either way, it's profoundly strange, and that's why almost 5 decades later, people are still talking about the WASP signal. Tabby's star, the star that breaks all the rules. Let's talk about something happening right now star that's been driving astronomers to distraction since 2011. Its official designation is KK 8,462,852, but most people call it Tabby's star, named after astronomer Tabitha Boyajian, who led the research team studying it. Tabby's star sits about 1,470 light-years away in the constellation Cygnus. At first glance, it appears completely ordinary, an F-type main sequence star, slightly larger and hotter than our Sun. Nothing about its spectrum or basic characteristics suggested it would become one of the strangest objects in the sky. But in 2011, the Kepler Space Telescope noticed something deeply weird. Stars dim sometimes. That's perfectly normal. When a planet passes in front of a star, from our perspective, an event called a transit, the star's light drops slightly. This is how we detect most exoplanets. The amount of dimming tells us the planet's size. When Earth transits the Sun from another star's perspective, the Sun's light dims by about 0.01%. Tiny but measurable with sensitive instruments. Jupiter, being much larger, would cause the Sun to dim by about 1%. This is the kind of regular, predictable, small dimming we expect from planets. Tabby's star doesn't do that. In 2011, its light dropped by 15%. Then it returned to normal. In 2013, it dropped by an astounding 22%. Then it recovered again. These dimmings were completely irregular, no predictable intervals, varying durations, different magnitudes each time. 20% is enormous, utterly unprecedented. To block that much light, you'd need something absolutely massive, comparable in size to the star itself. A planet the size of Jupiter would only block 1% of the star's light. Even a brown dwarf, a failed star, wouldn't block 22%. You'd need something as large as the star itself passing in front of it. The initial discovery triggered a frenzy of speculation. What could possibly be blocking this much light? This is where things got genuinely interesting and controversial. Someone suggested it might be an alien megastructure. The idea comes from a concept called a Dyson sphere, proposed by physicist Freeman Dyson in 1960. Dyson wondered what an advanced technological civilization would do if it needed enormous amounts of energy, far more than could be collected from a planet's surface. Eventually, he reasoned, They might build structures around their star to capture a significant fraction of its energy output. Not a solid shell that would be physically impossible, unstable under its own gravity, but a swarm of energy-collecting satellites orbiting the star at various distances. As this swarm orbited, it would block varying amounts of starlight, creating irregular dimming patterns. It would be unpredictable because the individual structures would be on different orbits. It would be large because you'd need an enormous array to collect significant energy. It would look exactly like what we were observing with Tabby's star. Now, before anyone gets too excited, let me be absolutely clear. Most astronomers don't think Tabby's star is an alien megastructure. The alien hypothesis was always the least likely explanation. But here's the remarkable thing: we had to consider it seriously, because we couldn't explain the observations any other way. That's how genuinely weird this star is. When your conventional explanations fail so completely that you have to seriously discuss alien megastructures, you know you're dealing with something extraordinary. So if it's not aliens, what is it? Scientists proposed several natural explanations. Perhaps there's a giant swarm of comets orbiting the star. If a family of comets passed in front of the star, their irregular shapes and dust tails would create uneven dimming patterns. This was a leading theory for a while because we know comets exist, we know they can be numerous, and we know they can create dust clouds. But the comet theory has problems. Where did all these comets come from? You'd need an enormous number, potentially thousands, to block 22% of the star's light. That's orders of magnitude more than typical comet populations around stars. And comets produce dust which absorbs blue light more than red light. If comets were responsible, we'd expect the star to appear redder when dim. Tabby's star doesn't do that. The color stays remarkably constant even during deep dimming events. Another theory suggested a recent collision. If two large objects, perhaps planets or large asteroids, smash together near the star, the debris cloud could block light irregularly as it spreads out and orbits. This might explain the massive dimming, but we'd expect to see excess infrared radiation from warm dust heated by the star. Multiple infrared surveys have looked for this signature. We don't see it. The debris would need to be cold, which is hard to explain if it's close enough to the star to transit across our line of sight. Some scientists suggested the dimming might be caused by the star itself. Perhaps it's a variable star with unusual pulsations. But Tabby's star doesn't show the spectroscopic characteristics of known variable stars. Its temperature and spectral lines remain stable. The dimming pattern is too irregular and too extreme to match any known type of stellar variability. Then in 2017, astronomers caught Tabby's star dimming again and observed it across multiple wavelengths, simultaneously ultraviolet, visible, and infrared light. What they found was intriguing. The dimming was more pronounced in blue and ultraviolet light than in red and infrared light. This color-dependent dimming is consistent with dust scattering. Small dust particles scatter blue light more effectively than red light. The same reason Earth's sky appears blue. So perhaps it is dust after all. But if so, where's it coming from? Why is there so much of it? Why is the pattern so irregular and unpredictable? The latest observations suggest Tabby's star might have a large, complex debris field around it, perhaps from a destroyed planet, a massive collision, or some other catastrophic event. The debris blocks light irregularly as it orbits the star in complicated patterns. This is currently the leading explanation, but it's not entirely satisfying. The full picture remains frustratingly unclear. We need more observations across more wavelengths, better models of dust behavior, and perhaps most importantly, patience as we watch this star over many years. And here's what makes this even more fascinating. Tabby's star is still doing it. We've now monitored this star for more than a decade. It keeps dimming in these weird, unpredictable ways. We have multiple datasets from different telescopes and observing campaigns. The phenomenon is absolutely real, not a measurement error, not a glitch in the instruments, not an artifact of data processing. Something is genuinely blocking the light from this star in ways that remain deeply puzzling. As of 2025, Tabby's star remains one of the strangest objects in the sky. Out of hundreds of billions of stars in our galaxy, this is the only one that behaves like this. We've never observed anything else quite like it. The Kepler mission monitored over 150,000 stars continuously for years. universe. Only one showed this behavior. That's how rare it is. Maybe one day we'll figure it out completely. Maybe we'll discover it's a natural process we just haven't encountered before, perhaps something that happens rarely in stellar systems, under specific conditions. Or maybe, just maybe, it's something else entirely, something we haven't even thought to consider yet. Odd radio circles. The universe's perfect mysteries. In 2019, scientists discovered something that absolutely shouldn't exist. They're called odd radio circles, or ORCs, and the name is perfect because they are genuinely odd perfect circles, visible only in radio wavelengths hundreds of thousands of light years across, surrounding distant galaxies. The discovery came from a team led by astronomer Ray Norris, using the Australian Square Kilometre Ray Pathfinder Telescope, ASCAP for short. ASCAP is sensitive to radio waves, allowing it to see the universe differently than optical telescopes. When the team processed their survey data, they found these strange circular structures. At first, they thought it was a processing error. Perfect circles are highly suspicious in astronomy because nature rarely makes perfect geometric shapes. Circles usually indicate problems with data processing, telescope artifacts, or interference. But when they checked the data carefully, scrutinizing the raw observations and reprocessing everything from scratch, the circles were still there, real, undeniable. They found 3 more. Then other telescopes confirmed them. As of 2025, we've discovered about a dozen ORCs. They're rare, incredibly rare, and their origin remains a complete puzzle. Let me describe precisely what we're seeing. Each ORC is a ring or shell of radio emission electromagnetic radiation at wavelengths of centimeters to meters, invisible to human eyes but detectable by radio telescopes. The ring is nearly circular, sometimes perfectly so, with dimensions that boggle the mind. At the center of each ORC sits a galaxy, usually an elliptical galaxy. The galaxy appears completely normal when observed in visible light. There's nothing obviously unusual about it, no dramatic star formation, no obviously active supermassive black hole, nothing that would explain the enormous radio rings surrounding it. The rings are absolutely enormous. Some exceed 1 million light-years in diameter. To put that in perspective, our entire Milky Way galaxy is about 100,000 light-years across. These rings are 10 times larger than our entire galaxy. They're structures on truly cosmic scales. Now, astronomers do see circular things in the sky sometimes. Supernova remnants can look circular. They're the expanding shells of debris from exploded stars. We've cataloged thousands of them. But supernova remnants are much smaller, typically tens of light-years across at most, and they're associated with recent stellar explosions in our own galaxy or nearby galaxies. ORCs are vastly larger and far more distant, hundreds of millions, or even billions of light-years away. They're definitely not supernova remnants. Planetary nebulae can also appear circular. These are beautiful shells of gas shed by dying stars, creating some of the most stunning images in astronomy. But again, they're much smaller, typically light-years across, not millions of light-years. And they're in our own galaxy. ORCs are clearly not planetary nebulae. Some galaxies have radio lobes, enormous jets of matter shot out by supermassive black holes. At their centers, these jets can create circular or elliptical structures when viewed from certain angles. We've observed many such radio galaxies, but ORCs don't match the characteristics of radio galaxies. The central galaxies don't show signs of the active supermassive black holes that would be necessary to create such structures. There are no visible jets, no evidence of the extreme energetic processes associated with active galactic nuclei. So what are they? Honestly, we don't know. Several theories have been proposed, each with its own problems. Maybe they're shock waves from massive explosions in the centers of galaxies. If a galaxy went through a period of intense star formation, creating and destroying millions of stars in a relatively brief period, or if its central black hole suddenly became active and then quieted down, it might create a blast wave that expands outward spherically over millions of years. This expanding wave could sweep up interstellar gas and accelerate electrons, creating the radio emission we observe as an ORC. But if that's the case, why don't we see more of them? Galaxies go through active phases all the time. Starburst galaxies and active galactic nuclei are relatively common. We should see these structures more frequently if they're created by common galactic processes. Another theory suggests orcs might be related to galaxy mergers. When the galaxies collide and merge, a process that takes hundreds of millions of years, all sorts of dramatic things happen. Gas clouds collide and compress, triggering enormous bursts of star formation. The supermassive black holes from both galaxies eventually merge, releasing enormous energy. Perhaps these violent events create shock waves that expand outward as spherical shells, becoming visible as orcs millions of years after the merger. But again, galaxy mergers are relatively common in the universe. We observe them at all stages of the process. If orcs were created by mergers, we'd expect to see many more of them. Some scientists have suggested even more exotic explanations. Maybe orcs are imprints of primordial events from the very early universe, remnants of processes that occurred shortly after the Big Bang. Maybe they're related to cosmic streams, hypothetical one-dimensional defects in spacetime predicted by some theories of the early universe. Maybe they're connected to dark matter in ways we don't understand. These ideas are highly speculative, venturing into territory where observational evidence is scarce. The truth is, we're still in the discovery phase with orcs. We've only known about them for a few years. We need more observations, more examples, better data across multiple wavelengths. We need to study the galaxies at their centers in more detail. Are there subtle signs of past activity we're missing? We need to search for orcs at different distances in different cosmic epochs to understand how they evolve over time. What makes orcs particularly fascinating is that they represent something genuinely new in astronomy. We've been studying the radio sky for decades, since the 1930s, when Karl Jansky first detected radio waves from the cosmos. We've discovered pulsars, quasars, radio galaxies, supernova remnants, and countless other radio sources. We thought we had a reasonably complete catalog of what kinds of things emit radio waves in space. But orcs only showed up when we built more sensitive radio telescopes with better imaging capabilities. They were always there, scattered throughout the universe, but we simply couldn't see them until recently. This tells us something profound about astronomy. The universe is full of things we haven't discovered yet, not because they're hiding or because they're particularly subtle, but simply because we don't yet have the tools sensitive enough to detect them. Every time we build a better telescope, every time we observe in a new wavelength range, every time we develop more sophisticated data analysis techniques, we find unexpected phenomena. Orcs are a perfect example. Nobody predicted them. Nobody was searching for giant radio circles around galaxies. They were a complete surprise, discovered serendipitously in a survey designed to map the radio sky for completely different purposes. And now astronomers are scrambling to figure out what they are and what they tell us about the universe. As of 2025, orcs remain unexplained real structures in the radio sky, patiently waiting for someone to decipher their secrets. The giant arc and big ring, structures too large to exist in 2021 and 2024. Astronomers discovered two enormous structures that fundamentally challenge one of cosmology's bedrock principles. These discoveries threaten to overturn our understanding of how the universe is organized on the largest scales. The first is called the giant arc. It was discovered by Alexia Lopez, a PhD student at the University of Central Lancashire. While analyzing data from the Sloan Digital Sky Survey, the giant arc is a structure composed of galaxies and galaxy clusters spanning approximately 3.3 billion light-years. Let me emphasize this. That's not the distance to the structure, that's how large the structure itself is. The structure is 3.3 billion light-years from one end to the other. To put this in perspective, light takes 3.3 billion years to travel from one end of this structure to the other. The entire observable universe is about 93 billion light-years across. This single structure spans a significant fraction of that incomprehensible distance. The giant arc is located about 9.2 billion light-years from Earth, meaning we're seeing it as it was 9.2 billion years ago, when the universe was only about one-third its current age. It appears as a curved arrangement of galaxy clusters, a giant arc in the sky, hence its name. The structure seems to follow a coherent pattern, as if the galaxies are arranged along some invisible framework. Then in 2024, the same research team found something else, the Big Ring. This is another enormous structure, roughly 1.3 billion light-years in diameter, also located about 9 billion light-years from Earth. And here's what makes astronomers deeply uncomfortable. It's in the same region of the sky as the giant arc at the same distance. Two enormous structures, both in the same cosmic neighborhood, both at the same epoch in cosmic history. That's not a coincidence you can easily dismiss. It suggests these structures might be related somehow, perhaps parts of an even larger structure we're only beginning to perceive. Now, why is this such a problem? Why are these discoveries challenging our understanding of cosmology? In cosmology, there's a fundamental principle called the cosmological principle. This principle, which underlies the entire standard model of cosmology, states that when you look at the universe on sufficiently large scales, it should appear roughly uniform. No matter which direction you look, you should see roughly the same density of matter, the same distribution of galaxies, the same large-scale structure. The universe should be homogeneous, the same everywhere, and isotropic, the same in all directions, at large scales. This principle isn't just philosophical, it's supported by observations of the cosmic microwave background radiation, which shows that the early universe was remarkably uniform, with density variations of only about 1 part in 100,000. It's built into Einstein's equations of general relativity as applied to cosmology. It's fundamental to our understanding of the Big Bang and cosmic evolution. But the giant arc and Big Ring challenge this principle directly. They're too large. According to calculations based on the standard cosmological model, structures shouldn't be able to grow larger than about 1.2 billion light-years. That's the theoretical limit based on how gravity has had time to pull matter together since the Big Bang. The giant arc is nearly 3 times larger than this limit. Even the Big Ring, at 1.3 billion light-years, is pushing uncomfortably against this boundary. If these structures are real, and they certainly appear to be, then either our theoretical limit is wrong, or something strange is happening with structure formation in the universe. Maybe the cosmological principle doesn't hold as well as we thought. Maybe the universe is lumpier on large scales than our models predict. Maybe there are processes we don't understand that can create structures larger than theory allows. Maybe our understanding of how gravity assembles matter on cosmic scales is incomplete. Some astronomers have questioned whether these structures are real, or just statistical flukes, patterns that appear to exist but are actually random arrangements that our pattern-seeking brains interpret as structures. When you look at the distribution of galaxies across the sky, you can sometimes see apparent patterns that don't represent physical structures, just chance alignments. But Lopez and her team conducted careful statistical analysis. They calculated the probability that the giant arc could be a random arrangement of galaxies with no physical connection. The result, about 1 in 6,000. That's pretty compelling evidence that the structure is real, that these galaxies are genuinely arranged in this arc pattern for physical reasons. The Big Ring statistics are even more convincing, and the fact that both structures are in the same region of space at the same distance makes a coincidence explanation much less likely. So what are they? One possibility involves something called baryon acoustic oscillations. In the early universe, before atoms formed, sound waves traveled through the hot plasma, creating pressure waves that left an imprint on how matter is distributed. These waves created a preferred scale, a characteristic size for structures. We can detect this signature in the distribution of galaxies today, but the giant arc and Big Ring don't match the expected scale from baryon acoustic oscillations. They're much larger, suggesting some other process is at work. Another possibility involves cosmic strings, hypothetical one-dimensional defects in spacetime, predicted by some theories of the early universe but never directly observed. If cosmic strings exist, they could act as seeds for structure formation, with galaxies forming preferentially along them, creating linear or curved structures. But cosmic strings are entirely speculative. We have no direct evidence they exist, and their properties, if they do exist, are highly uncertain. The most troubling possibility is that our cosmological model is incomplete. Maybe the cosmological principle isn't as robust as we assumed. Maybe the universe has large-scale structures that our models don't account for. Maybe at the very largest scales, billions of light-years, the universe is more complex. than our equations suggest. This doesn't mean the Big Bang theory is wrong. It doesn't invalidate decades of cosmological research. It means we might need to refine our understanding of how structure formed in the universe, how matter assembled into galaxies and galaxy clusters, and how these structures are distributed across space. This is how science works. You build models based on observations, make predictions, and test those predictions with new observations. When new observations don't quite match the predictions, you update your models. Sometimes it's a small adjustment. Sometimes it requires rethinking fundamental assumptions. As of 2025, the giant arc and big ring remain controversial. Some astronomers are convinced they're real structures that genuinely challenge the cosmological principle and require us to revise our understanding of large-scale structure formation. Others are more skeptical, suggesting they might be statistical artifacts, chance alignments, or misinterpretations of complex data. What's clear is that the universe at the largest scales is more complicated than we thought. These enormous structures, whether they ultimately prove to be genuine anomalies or something else, are pushing us to think more carefully about how the cosmos is organized, and whether our most fundamental assumptions about cosmic uniformity are actually correct. The boat's void. The Great Empty. Let me tell you about a place in the universe that's almost perfectly empty. It's called the Boat's Void, and it's one of the strangest features of the cosmic landscape. A region where galaxies should exist but simply don't. The Boat's Void is a region of space roughly 330 million light-years in diameter. To appreciate this scale, consider that our entire Milky Way galaxy is about 100,000 light-years across. The Boat's Void is more than 3,000 times wider than our galaxy. It represents an enormous volume of space, billions of cubic light-years. Based on the average density of galaxies in the universe, this volume should contain approximately 2,000 galaxies. That's what we'd expect if matter were distributed uniformly, as the cosmological principle suggests. But when astronomers survey the Boat's Void, they find only about 60 galaxies. The rest is empty or nearly so. It's not completely devoid of matter. There are those few dozen galaxies scattered throughout, presumably along with dark matter and probably some diffuse gas. But compared to what should be there, compared to the typical density of galaxies in the universe, it's remarkably void of visible matter. That's why we call it a void. The Boat's Void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. During a galaxy redshift survey, they were mapping the three-dimensional distribution of galaxies, measuring their distances and positions to understand the universe's large-scale structure. As their map grew, they noticed this huge empty region in the constellation Boats. Initially, they weren't sure if it was real. Maybe they had missed some galaxies. Maybe their detection methods weren't working properly in that region. Maybe there was some observational bias that created the illusion of emptiness. But follow-up observations with different telescopes and techniques confirmed it. The void is absolutely real. There really is this huge bubble of space with almost no galaxies. Now, voids aren't unusual in the universe. When we map the large-scale structure of the cosmos, we find that galaxies aren't distributed uniformly. Instead, they're ranged in a cosmic web, filaments and sheets of galaxies surrounding vast voids. Most voids are tens of millions of light-years across. They're pretty common features of cosmic structure, but the Boat's Void is special. It's much larger than typical voids. It's one of the largest known supervoids in the relatively nearby universe, and its very existence raises profound questions about how structure formed in the cosmos, and whether our understanding of that process is complete. Here's the fundamental issue. The universe started out almost perfectly uniform. We know this from observations of the cosmic microwave background radiation, which shows us what the universe looked like when it was only 380,000 years old. At that time, matter was spread almost evenly throughout space. There were tiny density variations, regions that were slightly denser or slightly less dense than average, but these variations were incredibly small, only about 1 part in 100,000. Over billions of years, gravity amplified these variations. Regions that were slightly denser attracted more matter gravitationally, becoming even denser. They eventually collapsed into galaxies and galaxy clusters. Regions that were slightly less dense lost matter to denser surroundings, becoming voids. Computer simulations of this process, which model billions of years of gravitational evolution, can reproduce the cosmic web we observe today. Filaments, clusters, and voids all emerging naturally from gravity acting on those initial tiny density variations. But the simulations also predict limits. Voids can only grow so large given the age of the universe, the strength of gravity, and the initial density variations. The boat's void is close to this theoretical limit. It's about as large as voids can get according to our models. That makes it particularly interesting because it's an extreme example, testing the boundaries of our understanding. If our models are correct, we shouldn't see voids much larger than the boat's void. If we do, it would suggest something is wrong with our models of structure formation. Perhaps the initial conditions were different than we think. Or perhaps gravity behaves differently on these enormous scales. Or perhaps there are processes we haven't accounted for. So far, the boat's void sits right at the edge of theoretical expectations. It's large, but not impossibly large. It fits within theoretical limits, but barely. That makes it worth studying very carefully, because structures at the limits of theory often teach us the most about whether our theories are correct or need revision. There's another intriguing aspect to the boat's void. The few galaxies inside it are weird. Astronomers have studied them in detail, and many show unusual properties. Some are forming stars at unexpectedly high rates. Some have irregular shapes or peculiar characteristics that differ from typical galaxies. In denser regions of the universe, it's as if the isolation has affected how these galaxies evolve. Think about it from the galaxy's perspective. If you're a galaxy in a dense region of space, you're constantly interacting with neighboring galaxies. You're pulling on them gravitationally. Sometimes you collide and merge, a violent process that dramatically changes both galaxies. You're exchanging gas with your neighbors through gravitational interactions. You're part of a busy cosmic neighborhood with constant interactions. But if you're a galaxy in the boat's void, you're essentially alone. Your nearest neighbor might be millions or tens of millions of light years away, so far that gravitational interactions are negligible. You're evolving in near-perfect isolation, without the gravitational harassment that galaxies in dense regions experience constantly. This isolation might fundamentally change how you evolve. Maybe you retain more of your original gas because no nearby galaxies are stripping it away through gravitational interactions. Maybe your star formation proceeds differently without the triggers that come from interactions with other galaxies. Maybe you develop unusual characteristics precisely because you're not subject to the influences that shape most galaxies. The galaxies in the boat's void represent natural experiments set up by the universe itself. They show us what happens when galaxies evolve in isolation, allowing us to understand which properties of galaxies are intrinsic and which result from environmental effects. But the fundamental question remains: why is the boat's void so empty? Why did this particular region of space end up with so few galaxies? The answer probably lies in the initial conditions of the universe. This region must have started out with a density slightly lower than average, one of those tiny variations visible in the cosmic microwave background. Over billions of years, gravity inexorably pulled matter out of the region toward denser areas, creating the void we see today. The process is slow but relentless. Matter flows from less dense to more dense regions, and over billions of years, the differences amplify enormously. But why was this region less dense to begin with? That's a deeper question that takes us back to the very beginning of the universe. It relates to whatever process created the initial density variations in the first moments after the Big Bang. Most cosmologists believe these variations originated from quantum fluctuations during the inflationary epoch, a brief period of exponential expansion right after the Big Bang. During inflation, the universe expanded so rapidly that quantum fluctuations were stretched to cosmic scales. These fluctuations were random, like static, but they became the seeds of all structure in the universe. Some regions ended up slightly denser by chance, others slightly less dense. Most fluctuations were small, but occasionally, just by random chance, you'd get a larger fluctuation, a region that was somewhat more or less dense than average. The Botsvoi might be the result of one of these chance larger fluctuations. In the initial conditions, a region that started out noticeably less dense than its surroundings. It's remarkable when you think about the causation. The emptiness we see in the Botsvoi today, 330 million light-years of nearly vacant space, originated as a microscopic quantum fluctuation in the first tiny fraction of a second after the Big Bang. That infinitesimal variation has been amplified over 13.8 billion years of cosmic evolution into this enormous supervoid. The universe is strange in this way. The smallest things can have the largest consequences given enough time. A quantum fluctuation lasting a fraction of a second can determine the structure of hundreds of millions of light-years of space billions of years later. The Botsvoi is a monument to this principle, a vast empty region whose existence was determined in the universe's first moments. The CMB cold spot, an anomaly in the afterglow of the cosmic microwave background. The CMB is the afterglow of the Big Bang, the oldest light in the universe. It's been traveling through space for 13.8 billion years, carrying information about what the universe was like when it was just 380,000 years old. Before that moment, the universe was opaque, filled with a hot plasma where photons couldn't travel far before scattering off free electrons. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, photons could travel freely. The universe became transparent. Those photons have been traveling ever since, stretched to microwave wavelengths by the universe's expansion. When we observe the CMB today, we see a faint microwave glow coming from every direction in the sky, with a temperature of about 2.7 to 5 Kelvin, just a few degrees above absolute zero. The remarkable thing about the CMB is how uniform it is. Measure its temperature in different directions, and you get almost exactly the same value everywhere. But there are tiny variations, hot and cold spots, where the temperature differs by about 1 part in 100,000. These variations aren't random. They're the imprints of density fluctuations in the early universe. Regions that were slightly denser appear slightly cooler in the CMB. These dense regions eventually became the galaxies and galaxy clusters we see today. The CMB is essentially a baby picture of the universe, showing what it looked like in its infancy. Satellites like COBE, MAP, and Planck have mapped the CMB with incredible precision, measuring temperature variations across the entire sky, with sensitivity better than 1 part in a million. These maps have revolutionized cosmology, allowing us to determine the universe's age, composition, and geometry with unprecedented accuracy. But when scientists analyzed these maps in detail, they found something unexpected. There's a region of the sky about 10 degrees across, roughly 50 times the apparent size of the full moon, that's significantly cooler than the surrounding areas. This is the CMB cold spot. It's not just slightly cooler, it's about 70 millionths of a degree cooler than the average. That might sound tiny, but in the context of the CMB's naturally tiny temperature variations, it's enormous. It's a statistical outlier, an anomaly that stands out clearly from the expected patterns. The cold spot is located in the constellation Eridanus. It's oval-shaped, spanning about 10 degrees by 5 degrees on the sky. Here's why this is strange. Based on our standard model of cosmology, the Lambda-CDM model, that describes the universe's composition and evolution, we can calculate the probability of such a large, cold region appearing by chance in the primordial density fluctuations. The probability comes out to about 2%. That means if you ran the universe 100 times with random initial conditions, drawn from the expected distribution, you'd expect to see a cold spot this large and this cold in about 2 of those 100 universes. Now, 2% isn't impossible. Unlikely things happen, but we only have one universe to observe, one CMB2 measure. We can't run the experiment again to see if we get the same result. So when we see something with 2% probability, we have to ask, is this just bad luck or is something unusual happening? Scientists have proposed several explanations, each attempting to account for why this particular region is so much colder than expected. One idea involves a supervoid, an enormous region of space with below average density of matter. If there's a huge void between us and the surface of last scattering, the region from which the CMB photons are coming. Those photons lose energy as they traverse the void through a subtle effect, called the integrated Sachs-Wolf effect. Here's how it works. When CMB photons enter a gravitational potential well, a region of higher density, they gain energy climbing out of the well. When they pass through a void lower density, they lose energy. If the universe weren't expanding, these effects would cancel perfectly, but because the universe is expanding, the void grows and becomes less dense while the photons are crossing it. This asymmetry means photons lose more energy than they gain, emerging cooler than they enter. So a supervoid could create a cold spot in the CMB, and indeed, astronomers have found evidence of a large void in the direction of the cold spot. But here's the problem. Even a very large void doesn't seem capable of producing a cold spot this large and this cold. The calculations suggest the void can only account for part of the observed effect. You'd need an absolutely enormous void larger than any we've observed to fully explain the cold spot. Another theory ventures into more exotic territory. Maybe the cold spot is evidence of a collision between our universe and another universe in a multiverse scenario. Some versions of inflation theory predict that our universe is just one bubble in an infinite foam of universes. If another universe bubble collided with ours early in cosmic history, it would leave a distinctive mark in the CMB, a circular region that's either colder or warmer than average. This is highly speculative. We have no independent evidence for a multiverse, and the collision hypothesis is difficult to test, but it shows how puzzled scientists are by the cold spot. When conventional explanations fail, people start considering exotic alternatives. A third possibility is simply that the cold spot is a statistical fluke. 2% probability means it's rare but not impossible. Rare things to happen. Maybe we just happen to live in a universe where this unlikely feature exists by chance. The challenge is that we only have one CMB to observe. We can't create multiple universes and see how many have cold spots. We have a single data point, our universe. This makes it genuinely difficult to know whether the cold spot is a meaningful anomaly, pointing to new physics, or just an improbable but natural occurrence. As of 2025, the CMB cold spot remains unexplained. It might be caused partly by a supervoid, but probably not entirely. It might be a statistical fluke, though that seems somewhat unsatisfying given its prominence. It might be evidence of exotic physics, multiverse collisions, cosmic strings, or something we haven't thought of yet. What's clear is that it's anomalous. It stands out in the CMB maps, larger and colder than our models comfortably predict. Until we have a convincing explanation, one that accounts for its size, its temperature, and its characteristics, it remains one of the strange, unexplained features of our universe. Przybylski star. The impossible elements. There's a star about 370 light-years away that breaks the rules of nuclear physics, or at least appears to. It's called Przybylski star, officially designated HD 1065, located in the constellation Centaurus. From a distance, it looks utterly normal, and a type main sequence star, about twice the sun's mass and 6 times more luminous. But when astronomers analyzed its spectrum, the light broken down into its component wavelengths, they found something that shouldn't exist. The star contains significant amounts of technetium and promethium, radioactive elements that decay so quickly they should have vanished billions of years ago. Let me explain why this is so deeply problematic. Stars create elements through nuclear fusion. In stellar cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. The process continues in the most massive stars, creating progressively heavier elements up to iron. Elements heavier than iron form primarily in supernova explosions and neutron star mergers, where extreme conditions provide the energy and neutrons needed for rapid element synthesis. When we observe heavy elements in a star's atmosphere, we assume they were present when the star formed. The star was born from a cloud of gas enriched by previous generations of stars' gas-containing elements from ancient supernovae. This is how the universe gradually becomes enriched with heavy elements over cosmic time. But here's the critical issue. Some heavy elements are radioactive and decay over time. Uranium, for example, has a half-life of about 4.5 billion years. Even after billions of years, some uranium persists. Thorium has an even longer half-life. These long-lived radioactive elements can exist in stars for billions of years. Technetium is different. It has no stable isotopes. All forms of technetium are radioactive and they decay relatively quickly. The longest-lived isotope, technetium-98, has a half-life of only about 4.2 million years. On human timescales, that seems long. On cosmic timescales, it's nothing. Przybylski's star is probably several billion years old based on its characteristics. If it formed with technetium in its atmosphere, that technetium should have decayed away billions of years ago. There should be none left, zero, not even trace amounts. Yet when astronomers observe this star's spectrum, they see clear, unambiguous evidence of technetium. Multiple spectral lines match technetium's fingerprint. They've also detected promethium, another radioactive element with no stable isotopes and a maximum half-life of about 18 years. For Przybylski's star to show promethium in its spectrum, the element must be continuously replenished, produced somehow, somewhere, all the time. This has been true since the star was first studied in detail in the 1960s by Polish Australian astronomer Antoni Przybylski, after whom it's named. For over 60 years, we've consistently detected these short-lived radioactive elements in this star's atmosphere. They're really there. So where are they coming from? Several theories have been proposed, but none is entirely satisfying. One possibility is that the star is somehow producing these elements on or near its surface, through unknown nuclear processes. Maybe there's a mechanism we don't understand, perhaps involving strong magnetic fields and particle acceleration that can synthesize technetium and promethium in the stellar atmosphere. But this seems unlikely. We have a very well-developed understanding of nuclear physics, and there is no known process that could do this in the relatively cool outer layers of a star like this. Another idea is that technetium and promethium are being brought up from deep inside the star. Perhaps nuclear reactions in deeper layers create these elements, and convection currents carry them to the surface where we can detect them. But the star's interior isn't hot enough for the exotic nuclear reactions that would be needed to produce these elements. The conditions required simply don't exist in stars like Przybylski's star. A third, more exotic idea involves super-heavy elements. In theoretical nuclear physics, there's a concept called the island of stability, a region of the periodic table, far beyond known elements where certain super-heavy nuclei might be relatively stable against decay. If such elements exist in nature, we've created some super-heavy elements in particle accelerators, but they decay almost instantly. Some might decay through chains that produce technetium or promethium as intermediate products. If Przybylski's star somehow contains super-heavy elements that are slowly decaying, they could continuously replenish the supply of technetium and promethium, maintaining detectable levels despite the rapid decay of these elements. This would explain the observations, but it's highly speculative. We've never observed super-heavy elements in nature. The island of stability is a theoretical prediction, not an established fact, and we have no idea how such elements could end up in a star's atmosphere. Przybylski's star has other peculiarities that add to the mystery. It has unusually high abundances of certain rare earth elements, holmium, dysprosium, europium, and others. These elements are much more abundant in this star than in the Sun, sometimes by factors of hundreds or thousands. The star is what astronomers call chemically peculiar. There are several classes of chemically peculiar stars, thought to arise from atmospheric processes that concentrate certain elements. Radiation pressure from the star's light and strong magnetic fields can cause some elements to sink or float in the stellar atmosphere, creating unusual abundance patterns. But even among chemically peculiar stars, Przybylski's star is exceptional. Its abundance patterns are extreme, and the presence of short-lived radioactive elements is unique. Some astronomers have wondered if Przybylski's star might be in a binary system, with an unseen companion, perhaps a neutron star or white dwarf. Maybe material from the companion, enriched with unusual elements, is falling onto Przybylski's star, bringing radioactive elements with it. But we see no evidence of a companion. The star's motion through space doesn't show the periodic wobble we'd expect from an orbiting partner. Spectroscopic observations show no signs of another star's light. If there's a companion, it's extraordinarily well hidden. As of 2025, Przybylski's star remains profoundly mysterious. For more than 60 years, It has displayed technetium and promethium in its spectrum elements that should have decayed away long ago. Either there's a nuclear process we don't understand, or the star contains exotic matter, or something is fundamentally wrong with our observations or interpretations. None of these possibilities is comforting. Each suggests gaps in our understanding of stellar physics, nuclear physics, or both. Przybylski star stands as a reminder that even seemingly simple objects just a star. After Olkin harbor deep mysteries that challenge our most fundamental theories. Oumuamua, the interstellar visitor on October 19, 2017. Astronomers at the Pan-STARRS telescope in Hawaii detected something moving through the solar system. Initially, they thought it was a comet or asteroid routine discoveries, but as data accumulated, they realized this object was profoundly different. They named it Oumuamua, a Hawaiian word meaning scout or messenger arriving first from afar. It was the first confirmed interstellar object to pass through our solar system, the first object we'd ever detected that originated from beyond our sun's influence, from the vast spaces between stars. Oumuamua came from interstellar space, approached from the direction of the constellation Lyra, passed through the inner solar system at tremendous speed, and headed back out into interstellar space. Because of its speed and trajectory, we knew immediately it wasn't bound to the sun gravitationally. It was just passing through, and we had only a few weeks to study it before it became too faint and distant to observe. What we learned during those weeks was absolutely fascinating and deeply confusing. First, its shape. Based on how its brightness varied as it tumbled through space, astronomers calculated that Oumuamua was extremely elongated. The best estimates suggested it was about 400 meters long, and only 40 meters wide, a length-to-width ratio of 10:1. Picture a cigar or possibly a thin pancake, depending on the exact three-dimensional geometry. This is highly unusual. Most asteroids and comets are roughly spherical or irregularly shaped, not long and thin like a cigar or flat like a pancake. Second, its surface. Oumuamua had a reddish color, similar to some objects in the outer solar system. This suggested its surface had been exposed to cosmic rays for a very long time, millions or billions of years, drifting through interstellar space. Cosmic rays gradually redden surface materials through chemical reactions, so the color told us Oumuamua was old. But here's what was strange. Oumuamua showed no signs of a coma. When comets approach the sun, solar heat vaporizes surface ice, creating a cloud of gas and dust called a coma. It's this coma that gives comets their characteristic fuzzy appearance and tails. Every comet we've ever observed close to the sun develops a coma. Oumuamua didn't, even when it passed close to the sun well inside Mercury's orbit. Subjected to intense solar heating, no coma appeared. No tail developed. It looked like a rocky asteroid, not an icy comet. This suggested it wasn't a typical comet made of ice and rock, but perhaps something more like an asteroid, solid rock or metal. But then came the truly weird part. Oumuamua's trajectory didn't quite match predictions based on gravity alone. After it rounded the sun and headed back toward interstellar space, it was moving slightly faster than expected. It was accelerating beyond what the sun's and planets' gravity would cause. This is actually normal for comets. When a comet's ice vaporizes, the escaping gas acts like tiny rocket thrusters, giving the comet a small push. This outgassing creates measurable non-gravitational acceleration. It's well understood and we observe it routinely in comets. But Oumuamua wasn't showing a coma, so what was pushing it? If gas was escaping, why couldn't we see it? Scientists proposed several explanations. Perhaps Oumuamua was outgassing, but in a way that didn't produce enough dust to create a visible coma. Maybe it was venting pure gas, perhaps nitrogen or hydrogen, that we couldn't detect with available instruments. Some observations suggested there might be very faint traces of gas, but it was hard to be certain. Another possibility involved radiation pressure, the push from sunlight itself. All objects in the solar system experience radiation pressure. Photons from the sun carry momentum, and when they hit an object, they transfer that momentum, creating a tiny push. For most objects, this force is negligible compared to gravity, but if an object is very thin and relatively light, more like a sail, then a rock radiation pressure becomes significant. Maybe Oumuamua wasn't a cigar-shaped object. Maybe it was more like a thin pancake or sheet, only a few meters thick but hundreds of meters across. If it was made of relatively low-density material, radiation pressure from sunlight could explain the observed acceleration, but this raises difficult questions. How would such an object form naturally? Natural processes generally don't create thin, rigid sheets of rock or ice hundreds of meters across. Gravitational collapse tends to produce roughly spherical objects. Collisions fragment objects into irregular pieces. Getting a thin, flat sheet seems extremely difficult through natural processes. This is where things got really speculative and controversial. In 2018, Harvard astronomers Avi Loeb and Shmuel Biala published a paper suggesting that Oumuamua might be artificial. Specifically, they proposed it could be a light sail, a thin, reflective sheet designed to be pushed by starlight. Similar to concepts for spacecraft propulsion we're developing here on Earth, such a sail could be a spacecraft or probe sent by an extraterrestrial civilization, either deliberately aimed at our solar system, or simply drifting derelict through interstellar space after its mission ended. The unusual elongated or flat shape, the lack of outgassing, and the acceleration from radiation pressure would all make sense. If Oumuamua were an artificial light sail, this suggestion generated enormous controversy. Most scientists were deeply skeptical. The alien hypothesis is always the absolute last resort in astronomy. You only seriously invoke extraterrestrial intelligence when you've exhausted all natural explanations, and there were natural explanations for Oumuamua, even if they required some stretching. Loeb argued that we should at least consider the possibility seriously. If Oumuamua were artificial, if we just detected alien technology passing through our solar system, it would be the most important discovery in human history. The fact that it's unlikely doesn't mean we should dismiss it without proper consideration. Extraordinary claims require extraordinary evidence, but we should be willing to gather that evidence rather than rejecting possibilities out of hand. Most astronomers think Oumuamua is natural, probably a comet with unusual properties, an asteroid with a weird shape, or perhaps a piece of a shattered planet from another star system. These explanations require fewer assumptions than invoking alien technology. Occam's razor suggests we should prefer the simpler explanation, when multiple explanations fit the observations. The fundamental problem is that we'll never know for certain. Oumuamua is gone, millions of kilometers away and receding at tens of kilometers per second. It's too far away and too faint to observe anymore. We had a few precious weeks to study it, and we didn't get all the data we wanted. If another interstellar object passes through the solar system, and statistically, they probably do regularly, we just haven't detected them until recently, we'll be better prepared. Telescopes will be ready, observation plans will be in place, and we'll gather much more detailed data more quickly. In fact, we've already detected a second interstellar object. In 2019, astronomer Gennady Borisov discovered an interstellar comet now called Borisov. This object is definitely a comet. It has a prominent coma and tail and behaves exactly like comets. In our solar system, Borisov is comfortingly normal, which actually makes it scientifically valuable. It shows that interstellar comets are pretty much like solar system comets, suggesting comet formation is a universal process. But Oumuamua remains unique. We've never detected another object quite like it. Maybe it was just a weird natural object, a statistical oddity. Maybe it was something more exotic. We'll probably never know with certainty. What's clear is that interstellar objects pass through our solar system regularly. The Milky Way contains hundreds of billions of stars. Each probably has asteroids and comets. Gravitational interactions eject some of these objects from their home systems, sending them drifting through interstellar space. Some of these objects, by pure chance, pass through our solar system. Now that we're watching carefully, we can detect them. Each interstellar object we detect teaches us about planetary systems around other stars. What kinds of objects form, what they're made of, how common different compositions are. Oumuamua, despite its mysteries, gave us our first glimpse of material from another stellar system. That alone makes it historically significant, regardless of whether it's natural or something more exotic. In June 2018, Telescopes around the world detected a brilliant explosion in a galaxy 200 million light-years away. The astronomical community labels such events systematically, and this one received the designation at 018 Cow. The cow part is just a random string of letters from the naming algorithm, but it stuck as a memorable nickname. At first glance, it seemed like a supernova and exploding star. Supernovae happen regularly throughout the universe. We detect dozens of them every year as automated surveys scan the sky for sudden changes. They're well-studied phenomena, and astronomers have developed detailed classifications based on their spectra and light curves. But as data accumulated, it became clear that at 2018 the cow was something else entirely. First, it was extraordinarily bright, about 10 to 100 times brighter than typical supernovae. That's an enormous difference, like comparing a candle to a spotlight. Second, it got bright incredibly fast. Most supernovae take weeks to reach peak brightness as the shock wave from the explosion expands, and the debris heats up. The cow reached peak brightness in just a few days. Then it faded rapidly. Most supernovae remain visible for months, slowly fading as radioactive decay provides energy to keep the debris hot and glowing. The cow faded in weeks. It was like someone flicked a cosmic light switch suddenly on, blazingly bright for a brief moment, then switched off. The spectrum was also bizarre. It didn't match any known type of supernova. The temperatures were extreme, tens of thousands of degrees, far hotter than typical supernovae. The material was expanding at a significant fraction of the speed of light, faster than most supernova ejecta. Astronomers were baffled. What kind of cosmic event could be this bright, this fast, this hot, and this utterly different from everything they'd seen before? As they searched archival data and continued monitoring the sky, they found more events with similar properties. These ultra-fast, ultra-bright transients appear to be an entirely new class of astronomical phenomenon. They're sometimes called fast blue optical transients, FBDs, named for their key characteristics. They're fast, reaching peak brightness and fading in days to weeks rather than months. They're blue, emitting copious ultraviolet light, indicating very high temperatures, and they're optical transients, meaning they appear and disappear in visible light. As of 2025, we've found several dozen FBDs. They're rare, much rarer than ordinary supernovae, or at least rarely detected. We're not sure if they're genuinely uncommon or if many simply go undetected because they fade so quickly that surveys miss them. Several theories attempt to explain these mysterious explosions. One idea involves the birth of black holes or neutron stars. When a massive star's core collapses, it forms either a black hole or neutron star, depending on the core's mass. This collapse releases stupendous energy, more than the sun will emit in its entire lifetime, released in seconds. Normally, most of this energy goes into blowing apart the star's outer layers, creating a traditional supernova. But perhaps in some cases, the energy is channeled differently. Maybe it creates a powerful jet that punches through the star's outer layers and shoots out into space. This jet, interacting with surrounding gas or the star's outer layers, could create a bright, fast transient that looks different from normal supernovae. Another theory involves tidal disruption events. If a star wanders too close to a black hole, the black hole's gravity can literally tear the star apart, a process called tidal disruption. The stellar material spirals into the black hole, heating to millions of degrees and emitting enormous amounts of energy as it falls in. We've observed tidal disruption events before. They're known phenomena, but most are slower than FBDs, taking months to peak and fade. Perhaps FBTs are a special type of tidal disruption, maybe a small black hole disrupting a white dwarf or neutron star. The different masses and densities might produce different dynamics, potentially explaining the speed and brightness of FBDs. A third possibility involves collisions between compact objects. Maybe a white dwarf collides with another white dwarf or a neutron star. Such collisions would release enormous energy in a very brief time, potentially creating an FBT. The collision would destroy both objects, converting a substantial fraction of their mass into energy according to Einstein's equation relating mass and energy. The truth is, we don't know yet. FBTs are so new as a recognized class of phenomena that we're still figuring out their basic properties. Each new detection provides more data, helping refine models and rule out some possibilities while supporting others. What's exciting about FBDs is that they represent something genuinely novel. Astronomy has been studying exploding stars for centuries. We've developed detailed, sophisticated models of different types of supernovae. We thought we had a pretty complete understanding of stellar death. Then along comes the and similar events breaking all the rules. They're brighter, faster, and fundamentally different from anything our models predicted. They forced astronomers to realize there are types of cosmic explosions they hadn't anticipated, phenomena that don't fit into existing classification schemes. This happens periodically in science. You think you understand a class of objects or events fairly completely. Your models work well. Observations match predictions. Then nature throws you a curveball, something that doesn't fit, that demands new explanations, new physics, new understanding. That's when science gets truly interesting, because it means there's something fundamental to learn. FBDs are showing us that stellar death is more diverse and complex than we knew. They're revealing processes we hadn't seen before. Physics operating under extreme conditions we're only beginning to comprehend. As telescopes improve and we monitor more of the sky more frequently, we'll likely detect many more FBDs. Each one provides clues about what creates them. Over time, patterns will emerge. We'll develop better models. We'll figure out what causes these bizarre explosions. But right now, in 2025, they remain mysterious, extraordinarily bright, extraordinarily fast transients that don't fit our understanding of how stars can explode. They're cosmic cows indeed. Rare, unexpected, and utterly fascinating. The Methuselah star. Older than it should be, there's a star about 190 light-years away. That presents an impossible problem. Its official name is HD 140,283, but astronomers call it the Methuselah star after the biblical figure, who supposedly lived 969 years. The comparison is apt. This star seems to be older than it has any right to be, possibly older than the universe itself. The star is visible with binoculars in the constellation Libra. It's a subgiant, meaning it's exhausted the hydrogen fuel in its core and has begun evolving off the main sequence. Stars like this are ancient, formed in the early universe when conditions were dramatically different from today. Studying them provides crucial information about cosmic history. Astronomers can estimate stellar ages using several methods. One examines the star's chemical composition. The universe began with almost pure hydrogen and helium, the only elements created in significant quantities during Big Bang nucleosynthesis. Over billions of years, stars have created heavier elements through nuclear fusion and scattered them into space through supernovae and stellar winds. These metals astronomers call all elements heavier than helium metals gradually accumulate. In the interstellar medium, a star with very low metallicity probably formed early, before many generations of stars had enriched space with heavy elements. The Methuselah star has extremely low metallicity, about 250 times less iron than the Sun. This strongly suggests it formed in the early universe when heavy elements were scarce. Another method examines the star's nuclear fuel consumption. Stars fuse hydrogen into helium, then helium into heavier elements. The rate depends on mass and composition. By observing temperature, luminosity, and composition, you can estimate how long the star has been burning and therefore its age. When astronomers applied these methods to the Methuselah star, they got an uncomfortable result. Approximately 14 billion years old, with uncertainties that overlap uncomfortably with the universe's age itself. Here's the problem. The universe is only 13.8 billion years old. We know this with high confidence from multiple independent measurements. The cosmic microwave background, the expansion rate Hubble constant, the ages of the oldest star clusters, they all converge on about 13.8 billion years. How can a star be 14 billion years old in a 13.8 billion year old universe? The formal uncertainties technically allow for ages just barely younger than the universe, but it's uncomfortably tight. The star appears to have formed very soon after the Big Bang, so soon that there's barely any wiggle room. Initially, some suggested maybe our measurement of the universe's age was wrong, but as measurements improved dramatically over the past 2 decades, the universe's age became increasingly certain. It's definitely around 13.8 billion years with uncertainties of only about 1%. So the issue must be with the star's age estimate. But how could we be wrong? The methods are well established based on solid physics. The key is understanding the uncertainties. The Methuselah star's age is around 14 billion years, but with error bars of roughly plus or minus 700 million years. This technically allows it to be as young as about 13.3 billion years. If the star formed within the first few hundred million years after the Big Bang, as soon as the first stars could form, it could be that old. But even this is uncomfortable. The very first stars were different from modern stars. They formed from pure hydrogen and helium with essentially no heavy elements. These population E stars were probably very massive and short-lived. The Methuselah star doesn't match the profile of a first-generation star. It has small amounts of heavy elements, consistent with being a second-generation star formed from gas enriched by the first supernovae. But second-generation stars couldn't have formed immediately after the Big Bang. It would take time for first-generation stars to live, die, and scatter heavy elements, perhaps a few hundred million years. So the Methuselah star probably formed at least a few hundred million years after the Big Bang, which would make its maximum possible age about 13.5 billion years or less. Yet observations persistently suggest it's older. Several possibilities exist. Perhaps our models of low metallicity stellar evolution are subtly wrong. Maybe these ancient stars burn their fuel differently than we think, making them appear older than they are. Maybe there's a process we don't understand affecting their nuclear burning rates. Another possibility involves distance. Age estimates depend on knowing the star's luminosity, which requires knowing its distance. Distance measurements come from parallax, measuring how the star's position shifts as Earth orbits the Sun. The Gaia satellite has measured parallaxes for billions of stars with unprecedented precision, including the Methuselah star. But some uncertainty remains. If the distance is slightly different than measured, the age estimate changes. A third possibility is simply that the true age is at the low end of the uncertainty range, and we're seeing statistical fluctuation. When you measure something with uncertainty, sometimes the true value is near the edge of the error bars. Maybe the Methuselah star is really 13.5 billion years old, and the higher estimate is just unlucky statistics. As of 2025, the Methuselah star remains uncomfortably old. Astronomers continue refining measurements, hoping to resolve the tension. The star serves as a crucial test of our understanding both of stellar evolution and of cosmic chronology. It's also a reminder that even seemingly straightforward measurements can harbor subtle complications. Determining a star's age seems simple in principle. Observe its properties, compare to models, calculate age. In practice, it requires understanding stellar structure, nuclear physics, chemical evolution, distance determination, and more. Small errors in any of these can propagate into significant uncertainties in the final age estimate. The Methuselah star stands as one of astronomy's persistent puzzles, a star that, according to our best measurements and understanding, seems to be older than the universe itself. Of course, it can't actually be older. Something about our measurements or models must be slightly off. But figuring out exactly what is taking time and considerable effort until we resolve this mystery. The Methuselah star continues to remind us that even the most fundamental questions, how old is this star? How old is the universe? Can have surprisingly complicated answers. Conclusion: living with cosmic mysteries, all these strange discoveries might seem unrelated at first glance. A radio signal from 1977, a star that dims irregularly, giant radio circles around distant galaxies, structures too large to exist according to theory, nearly empty voids where galaxies should be, cold spots in ancient light, radioactive elements persisting where they shouldn't, an interstellar visitor with peculiar properties, explosions brighter and faster than any known type, a star apparently older than the universe. They appear to be completely separate mysteries, unconnected phenomena scattered across different areas of astronomy. But perhaps they're not. Perhaps they're all telling us the same fundamental thing. The universe is more complex, more surprising, more strange than our current models can fully capture. There are processes, phenomena, or physics we don't yet understand. Each mystery individually is just an oddity, an anomaly that demands explanation. But taken together, they paint a picture of a universe still capable of surprising us, still showing us things we didn't expect, still challenging our assumptions about how reality works. This is actually normal in the history of science. When you're on the edge of understanding something genuinely new, you start seeing anomalies, things that don't quite fit the existing framework. At first, they seem like isolated problems, troublesome outliers. But eventually, someone connects the dots, recognizing that these anomalies are symptoms of something bigger, something we haven't yet grasped. That's how relativity was discovered. In the late 1800s, there were several annoying problems in physics. Mercury's orbit didn't quite match Newtonian predictions. The speed of light seemed mysteriously constant regardless of measurement method. These seemed like separate issues requiring separate ad hoc fixes. Then Einstein came along and showed they were both explained by the same new framework. Relativity connected the dots, revealing that space and time were not the absolute quantities Newton assumed but were flexible, relative, interconnected. Suddenly, multiple mysteries made sense as consequences of a deeper principle. Maybe something similar is happening now with these cosmic mysteries. Maybe they're pieces of a puzzle we don't yet see completely. Someday, someone might develop a new theory or discover a new phenomenon that explains multiple mysteries at once, revealing connections we didn't recognize. Or maybe not. Maybe each mystery has its own separate, mundane explanation. Maybe the WOW signal was a comet. Maybe Tabby's star has a dusty debris field. Maybe orcs are just shock waves from galactic explosions. Maybe the giant arc is a statistical fluke. Maybe Przybylski's star has some exotic but natural nuclear process. Maybe Oumuamua was a nitrogen iceberg. Maybe FBTs are just a rare type of supernova we hadn't seen before. Maybe the Methuselah star's age is just at the edge of uncertainty. We won't know until we gather more data, develop better theories, and test them rigorously against observations. That's the scientific process. Propose explanations, make predictions, test predictions, refine or discard theories based on results. But the possibility that these mysteries are connected, that they're all pointing towards something fundamental we're missing about how the universe works, is genuinely exciting. It suggests we might be on the cusp of a breakthrough, a new understanding that will explain not just one mystery but several. This is what makes astronomy so fascinating right now. We have better telescopes than ever before. We're gathering more data than any previous generation of astronomers could have imagined. We're finding unexpected phenomena regularly, and some of those phenomena genuinely puzzle us, defying explanation despite our best efforts. That's not a failure of science. It's science working exactly as it should. We observe reality carefully, measure it precisely, and honestly acknowledge when observations don't match our expectations. Then we work to understand why, developing new theories and conducting new observations until the picture becomes clear. These mysteries remind us of how much we still don't know. Despite centuries of astronomical observation, decades of space exploration, and incredible advances in technology and theory, the universe still surprises us. It still presents phenomena we can't easily explain. It still challenges our understanding. That's both humbling and exhilarating. Humbling because it reminds us that we don't have everything figured out, that nature is under no obligation to make sense to us on our schedule. Exhilarating because it means there's still so much to discover, so many questions to answer, so many mysteries to solve. The strangest things we've discovered in space are strange precisely because they don't fit our current understanding. They're outliers, anomalies, puzzles. But puzzles can be solved. Maybe not immediately, maybe not easily, but eventually with enough observation, enough thought, enough creativity we figure things out. That's the story of science. Mysteries gradually being illuminated, revealing a universe stranger and more wonderful than we imagine. The WOW signal, Tabby's star, orcs, the giant arc, the boat's void, the CMB cold spot, Przybylski's star, Oumuamua FBDs, the Methuselah star. These are current chapters in that ongoing story. Someday, they'll be solved. They'll be explained. They'll fit into our understanding of how the cosmos works, and when that happens, when these mysteries finally make sense, we'll undoubtedly have discovered new mysteries to replace them, because the universe is vast and complex and ancient, and we've barely begun to understand it. The cosmos is full of strange things. Some we've found, many more we haven't. Each discovery, each mystery, each unexplained observation is an invitation to wonder, to question, to explore more deeply. We're fortunate to live in an age when we have the technology to detect these mysteries, the knowledge to recognize them as anomalous, and the intellectual framework to investigate them scientifically. Previous generations could only wonder about the sky. We can measure it, analyze it, try to understand it. And when we encounter something we can't explain, when the universe shows us something genuinely strange, we don't give up. We don't dismiss it. We take it seriously. We study it carefully. We try to understand it, because that's what science is. The patient, careful, honest effort to understand reality as it actually is, not as we wish it to be or expect it to be. The strange discoveries in space aren't problems to be frustrated about. They're opportunities to learn something new, something fundamental, something that might transform our understanding of reality. So when you look up at the night sky tonight, remember, out there in that vast darkness, strange things are happening. Things we've detected but don't understand. Things we haven't detected yet. Things that challenge everything we think we know. And somewhere, right now, an astronomer is puzzling over data that doesn't make sense, trying to understand one of these mysteries, pushing against the boundaries of human knowledge. That's the ongoing adventure of astronomy, exploring the cosmos, discovering strange things, and working to understand them. The mysteries are real. The quest for answers continues, and the universe, wonderful and strange, awaits our questions.